Welcome back. In the last episode, we introduced how temperature affects air density, engine performance, and weather stability. Now, we'll dive deeper into adiabatic processes, heat transfer, and how temperature shapes real-world flight conditions every day. Let's start with adiabatic processes. This refers to temperature changes that occur without adding or removing heat from the air. When air rises, it expands due to lower pressure and cools adiabatically. When it sinks, it compresses and warms. The dry adiabatic lapse rate, DALR, is about 3 degrees Celsius per 1,000 feet. That's how unsaturated air cools as it rises. But once the air cools to its dew point, condensation begins, releasing latent heat, which slows further cooling. At that point, the moist adiabatic lapse rate, MALR, takes over, usually around 1.5 degrees Celsius per 1,000 feet. This slower cooling is due to the heat released during condensation. It's why moist air rises more easily and forms clouds more readily. These lapse rates play a big role in atmospheric stability. If rising air remains warmer than the surrounding air, it continues to rise, causing instability, turbulence, and possibly cloud development. If it becomes cooler than the air around it, it sinks, leading to stability. Let's visualize it. A parcel of air rising through a cooler surrounding atmosphere is unstable, it climbs rapidly. But if the atmosphere is warmer than the rising air, it resists vertical motion. That's a stable layer, often seen in stratus clouds or inversions. Stability affects cloud types and turbulence. Unstable air leads to cumuliform clouds, with strong vertical development and turbulence. Stable air produces stratiform clouds, smooth rides, and gentle precipitation. Knowing the stability profile is key for comfort and safety. Now, let's explore heat transfer mechanisms. There are 3 main types. Conduction, transfer through direct contact, like warm air heating the runway surface. Convection, vertical transfer via rising air currents. Radiation, energy transfer via electromagnetic waves, like solar heating of Earth's surface. Each mechanism impacts flight. Convection is responsible for thermals, which can create bumpy air, especially in the afternoon. Radiation cooling at night can lead to temperature inversions, fog, or dew. Conduction affects surface conditions and runway temperature. Let's apply this to aviation. Thermals are common during late morning to mid-afternoon, especially in dry areas. Radiation fog can form after sunset when the surface cools rapidly under clear skies. Temperature inversion layers can cause reduced visibility and wind shear on approach. We also use isotherms on weather charts, lines connecting points of equal temperature. Analyzing their spacing and orientation helps identify frontal boundaries, inversions, and jet stream zones. A sharp temperature gradient equals potential instability. Surface temperature charts help pilots plan fuel burn, engine performance, and expected density altitude. Jet pilots check upper air temperature charts to avoid severe turbulence or choose the most efficient cruise level based on SAT. Let's not forget about temperature and wind. Temperature differences drive pressure differences, which in turn generate wind. Greater contrasts equals stronger pressure gradients equals faster winds. That's why we see stronger winds near fronts or mountain ranges. And yes, mountains modify temperature patterns too. As air rises along a slope, it cools adiabatically and may reach dew point, forming clouds and precipitation. On the lee side, the air descends and warms, creating dry, warm FON winds. This warming effect on the downwind side of mountains can cause temperature spikes, turbulence, and reduced humidity. It's why glider pilots love mountain waves, but it can catch others off guard, especially near terrain. Another critical aspect is diurnal variation, temperature changes from day to night. These affect air density, thermal activity, and visibility. A warm afternoon may cause thermals and bumps, while early morning offers calm air but a risk of radiation fog. Let's talk performance again. A difference of just 5 degrees Celsius in OAT can significantly increase takeoff distance, especially at high elevation airports. Always use the most current temperature in your performance charts, not just the forecast. Also, temperature influences fuel efficiency. At higher altitudes, colder air reduces drag and improves engine performance up to a point. But too cold, and fuel may need heating. Most FMS systems factor this in during cruise planning. During descent, Temperature inversions can cause wind shear and low-level turbulence, especially near the ground. Expect sudden changes in speed or direction, and always brief passengers and prepare the aircraft accordingly. Let's take a real-world scenario: you redescending into an airport at sunrise after a cool, clear night. There's a strong inversion near the surface. Expect calm air aloft, but potential low-level wind shear or even fog patches close to the runway. Plan your approach accordingly. Now, how do pilots monitor temperature in flight? Most aircraft display OAT on the MFD or PFD. Larger aircraft calculate SAT and TAT for performance monitoring. Understanding these values helps adjust thrust, anticipate turbulence, and manage anti-ice systems. Let's also touch on temperature in climb profiles. Warmer air aloft means less performance than expected, and cooler air may improve rate of climb. That's why climb performance charts often include temperature adjustment columns. For IFR flight planning, freezing levels are critical. You need to know where the OAT drops below 0 degrees Celsius, especially when flying through clouds or precipitation. Many weather sources now give freezing level charts or tools to estimate icing risk by altitude. Pilots also monitor dew point spread, the difference between temperature and dew point. A small spread, within 3 degrees Celsius, means fog or clouds may form soon. Use this during pre-flight to predict morning fog or evening haze at your destination. Temperature is also vital for autopilot performance, especially in older systems. Temperature gradients can alter pitch trim or vertical speed responses. Modern FMS handle this well, but it's still good to monitor. And finally, let's not forget temperature's role in pressure systems. Heating creates low pressure, and cooling leads to high pressure. This is the foundation of weather systems. Cold fronts, warm fronts, and cyclogenesis all rely on temperature differences. Let's recap. Adiabatic cooling warming shapes weather and stability. Temperature influences density, engine performance, and turbulence. Heat transfer mechanisms explain fog, thermals, and inversions. Mountains and time of day change local temperature behavior. Knowing OAT, SAT, and freezing levels helps you plan safely. In our next episode, we'll dive into humidity. We'll explain how moisture in the air affects performance, visibility, and weather, plus how to read dew point and predict cloud formation. It's the next essential piece in understanding the flying atmosphere. See you in Meteorology number 14, Humidity, Part 1.